Hello everyone and welcome to the first lecture of this course, which is the analysis and design of staircases. So in this course what we will do is that we will be going through the analysis and design of three different types of staircases. These three different types of staircases are the most common types of staircases used in civil engineering. So these three staircases are my two-flight staircase, my three-flight staircase, and spiral staircases. So we all know that in order for one to go from one floor to the other, one can use one of different options, which is either an elevator, which is the most common used method, two, a ramp, three, we can use an escalator, and four, we can use the staircase, which is not the most common method used voluntarily by everyone. However, in this course, we are going to learn more about these staircases, the analysis and design of these staircases, the behavior, and the structural components that are within my stairs. So if you look at this image here, so let's open it from here to get a better look at it. Okay, we can see that in order for us to go from one floor to the other, we need to go up the stairs, then we are going to reach our landing, or basically you can call it your resting spot, and then you are going to go up the stairs again to reach your upper floor. So basically we said we have a flight, landing, and a flight again. Now this picture here represents our three-flight staircase, whereas this image here is what represents our two-flight staircase. In this video, we are going to cover the first type of staircase that we have, which is our two-flight staircase. Now, if you want to talk about our staircase, we can draw our stairs as different components. We can draw our stairs either as a shell element or a beam, as a frame element or a beam, so basically as a 2D element. So it goes something like this. We have our support, then we have our landing, stairs, landing, and another support here. So here we are representing this as a beam with a width of 1 meter and a thickness equivalent to the thickness of my staircase. Now we are talking about 1 meter because we usually reinforce per meter. Now we need to know, what does these two supports represent? What do they represent for me? What are these two supports? So to better understand these two supports, we are going to talk more about them later on in a few minutes. Now, another way we can represent our beam is as a shell element, or basically as an area element, and we can find my M11, M22, and reinforce my staircase accordingly. However, as a structural engineer, what we need to do is we need to try and simplify our problem as much as possible. So if we can avoid drawing our model or our staircase as a 3D model, and we can resort to a 2D model, so we can just go to SAP, draw our 2D model, and find the moment that is being applied here and find the reinforcement required, and this way we would have simplified our problem by a huge amount. So this is something that we need to take into consideration. Okay, so now let's go through the structural components that are within my staircases. So if we look at this image here, we can see that we have column, and we have a beam here right behind my landing as well as here, and we have our slabs, which can be split into two parts. We have our landing slab and we have our flight slab. So let's just write them here. So the structural components are basically 1 my columns, 2 beams, and 3 my slabs, which can be for landing and flight. Okay, now in order to design our staircase, we have to take specific steps to do so. So the first step we usually take is the pre-dimensioning of our structural components. So basically finding the dimensions of my beam and the preliminary thickness of my slab. Now to find the preliminary thickness of my slab, we're going to go to the ACI code. So let's open it here. So the ACI code for minimum thickness of solid non-pre-stressed one-way slabs. We are going to use this table in order to find the thickness of my staircase. So the ACI code is asking us about our support condition. Is it simply supported? Is it one end continuous? Is it both ends continuous, or a cantilever? So we have to determine the support condition of my staircase in order to know or to determine the preliminary thickness. Now, how can we find this out? We said that before, we need to better understand the supports that I have within my staircase. These two supports, what do they represent here? What are they? So we need to better understand the overall image of my staircase in order to know the support behavior of my structural components. So in order to do that, we have to divide our staircase into different strips. So let's go to this image here, and this image divides my staircase into different strips. And if we can see, if we're looking at this red strip here, we can see that the load is distributed along the location, which is landing, flight, landing. And then this load is transferred from the landing here to this beam here, and then it is transferred from the beam to my column. So this is the way my load is being distributed. So basically, if we go back to this image here, so we have this support, then the landing, then stairs, then landing, then this support. So I only have supports at start and at end. I do not have any supports, any intermediate supports. This is one thing that we can conclude for sure. Now, the second question is, or the second conclusion that we have to go to is, what are these two supports? What are they? So these two supports are basically my beams, because we said that we have our landing, stairs, landing, and then my landing transfers the load to my beam and from my beam to my column. So the reaction here, I'm going to have my reaction in kilonewtons per meter. So if I want to draw the section of my beam, it's going to be like this. This is my beam, and I'm going to have a distributed load here, and the magnitude of this load is going to depend on which beam am I taking. Am I taking the bottom beam, or am I taking the top beam? And in addition to that, the moment here is going to be WL squared over 2 equals WL squared over 8, not 2. And this using this moment, we can find our bending moment diagram, and we can find the reinforcement required within my beam and the max moment location within my staircase, which is usually along mid span. So now that we understood the supports that I have here and the support locations within my staircase, we can go back to our ACI code. So basically, we said we do not have any intermediate supports. We just have a support at start and a support at end. So we are going to take our slab as a simply supported slab. So to find my thickness, my thickness is going to be L over 20. Okay, so again, I said that the thickness that we have is going to be L over 20. Now, what is the length that I'm going to take into consideration here? So, if we draw this again, the length is the total length of my staircase, which is my landing plus my staircase plus my landing. And it is not the projected length of my staircase, it is the diagonal length of my staircase that I need to take into consideration. So if we go here to this image, this is going to represent our example that we are going to take into consideration for our two-flight staircase. So if you look at the L here is going to be 1.5 times 2, okay, plus 2.7 over cosine alpha. This is my L, and I'm going to divide this by 20 to find the thickness. Now, why did I go for 2.7 over cosine alpha, and what is alpha? So to find alpha, basically, we have this as 2.7 from my image, and we have this as 1.5. So my alpha is basically tan alpha equals 1.5 over 2.7. So if I want to find alpha, implies alpha equals 30 degree, which is tan inverse of 1.5 over 2.7. Now this value here is 2.7 over cosine alpha, because if I go for cosine alpha here, this is x, this is the value that I want. So x, so cosine alpha equals 2.7 over x. So implies x equals 2.7 over cosine alpha. We can also take it as 1.5 over sine alpha. It's the same thing. You can go for whichever number that you want. They both work, because sine alpha equals 1.5 over x, so x equals 1.5 over sine alpha. Now if we go back here, L equals 2 times 1.5, which is 3, plus 2.7 over cosine 30, which is going to be 3 plus 3.11 equals 6.11. So implies my thickness is going to be 6.11 over 20, which is going to be around 0.3 meters. Now, as a structural engineer that has a lot of experience on site, you would know that a thickness value of 0.3 meters is actually too big. It's not a convenient value. So usually when you follow the code gives you a value that will for sure 100% satisfy your deflection criterias and any check criterias that you need to go for. However, what we can do is we can reduce this value. So instead of taking 0.3, we will take 0.2 meters and check for deflection and check for all of our checking criterias, and make sure if all of these criterias are satisfied, then a 0.2 meter value is much more convenient than a 0.3 meter thick stairs. So this is what we're going to do. We are going to go for a 0.2 meter stairs of thickness 0.2 meters. Now we need to know that about this thickness here. Which thickness did we just find? So if we draw our staircase here, something like this. Okay, so we have this thickness here, which is T1, and we have another thickness here, which is T2. Okay, so we know that the concrete here within my step or within my stairs will play a role in the flexural capacity of my stairs. So what I will do is that I would take half the thickness of my riser and include it into my thickness calculation and find the T average. So my T will be T average equals T1, which we just found, 0.2, plus the riser or the stair thickness, which we usually take as 0.15, divided by 2, which will give me a value of 27. Just let me erase this. 27.5 centimeters. So this is the value that we are going to take. We have found our dimensions now for our staircase. We still have the dimensions of my beam left. So when we talk about my beam, we are going to consider a drop beam. And this drop beam is going to have a thickness or a drop that is equivalent to 2 times my slab thickness. So 2 times 27.5 is going to be around 55. We are going to take it as 50 centimeters. And the width of my beam is going to be equal to my column's width. So this value here, we are going to take it as 20 centimeters, because when we are working with SAP, we are going to consider our column as a point support, and we are not going to actually draw our columns. So our beam dimensions are going to be 20 centimeters by 50 centimeters. So this way we found the dimensions of both my beams and my slab. We have one last thing to cover before we go into SAP and start working with our staircase model, which is my loads. So the loads that I will be working with, one, are my live load, which we are going to take as 5 kPa, and 2, we have my dead load, which is the weight of my tiles plus weight of riser over 2. Why? Because we said that we included half of my riser's thickness into my slab calculations. So here I'm going to take the other half in my dead load calculations. So here the weight of my tile, or basically we can call it the weight of my block, is going to be, so let's put here dead load or superimposed dead load, equals my tiles plus covering, which usually make up to around to a value of 2.5 kPa, plus my riser over 2. Now the weight of my riser is gamma concrete, because my riser is made of concrete, times thickness over 2. So this is equal to gamma concrete times thickness over 4, which is equal to 25 times the thickness that I have, which is 0.15, over 4. So here, if we want to go back to my superimposed dead load calculation, it's going to be equal to 2.5 kPa plus 25 times 0.15 over 4, which will give me a value of 3.5 kPa. So this is my superimposed dead load that I'm going to input to SAP, and my live load value is going to be 5 kPa. So this is basically it for the introductory lecture. Behind the pre-dimensioning, we better understood the behavior of our staircase. How are the loads distributed? What are or what is our support system that is within my staircase, and the dimensions of both my beams and my slab. So now we can move to SAP and start preparing our model and analyze and design our staircase system. So that is what we are going to do in our next video. So I'll see you then.